All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. This is AP Chemistry. We're in the thermochemistry unit, and we're in section 6.2 now, which is energy diagrams. Now, the nice thing here, ladies and gentlemen, since we looked at kinetics, we've actually already looked at energy diagrams. So this is going to be a very quick video. It's just going to be a very quick recap of some of the high points that we looked at in the previous unit. Should be things that we already know. So let's go ahead and just dive in. I'm thinking this will be done in like 5 minutes. So here we go. So again, we've seen energy diagrams and we've seen it shows reaction progress and potential energies on the y-axis. And so we can note that the starting and ending points are going to represent your reactants and products, right? And so what we need to be able to do is from an energy diagram like what's been provided, identify whether or not the process is endothermic or exothermic, right? And so if we're looking at reaction A, for example, we notice that in order to go from reactants to products, the potential energy goes up. Products are higher in potential energy than reactants. That means reaction A is endothermic. For reaction B, we see that the reactants are actually higher in energy than the products. So as this process takes place, the products are formed, energy is released. And so for reaction B, that would be an example of an exothermic process. Nothing new there, right? We also know that we have activation energy. We know that for given reactions, they have to overcome that in order for the reaction to start. Now, your activation energies can come in various shapes and sizes. You can have a high activation energy, you can have a low activation energy. And if you look at it in both of these cases, these are both exothermic processes, just one has a significantly lower activation energy than the other. Just keep that in mind. Activation energy, this is the energy that's needed to start your chemical process. All right. And so here, they want you to consider the following reaction. You've got 2ClF3 plus 2NH3 produces N2 plus 6HF plus Cl2, and it's got a delta H of negative 1,196 kilojoules per mole. And it says draw a reaction pathway diagram for this reaction and label the products, reactants, and delta H. So for this, they want you to just be very general. They didn't give you enough information to plot specific energy. So really, all you're going to be doing, ladies and gentlemen, you've got on your x-axis reaction progress. You should have potential energy on your y-axis. And in this case, because it's negative delta H, what we should show is we should show that the reactants are going to be higher in energy. It doesn't say anything about the activation energy, so we're just going to do something like this, something like that. So here's our reactants. Here's our products. And delta H is right there. Right. So there you go. Simple as that. All right. And then you can also have catalyzed versus uncatalyzed reactions. Remember, a catalyst, what it essentially does is it lowers the activation energy of your process, allowing the reaction to speed up. Now, it's important to recognize that what's being changed is the activation energy. That's what's being changed. But please note that in this particular process, delta H stayed the same. So EA changes, but then the energy of products, energy of reactants, and delta H stay constant, stay the same. Right? That's really the big thing you need to note from a catalyzed reaction. Yes, there might be some changes to the activation energy, but the other energy values stay the same. All right. And that, ladies and gentlemen, is all we needed to talk about from an energy perspective of energy diagrams. We've already seen them. hopefully this is just a real quick review. Thank you guys for joining me, and I'll see you guys again soon. Take care.